Greetings. We are the SJC Gators from San Jacinto College. Our Texas Space Grant Consortium Design Challenge is to create a solar concentrator for extraterrestrial use. The SJC Gators is made up of 3 team members, Daniel Guerra, Ryan Alinger, and myself, Michael Kruger. Our faculty advisor is Dr. Nathaniel Wiggins, and we have 2 mentors, Mr. Christopher Mendel and Mr. Houston Green. According to the Artemis mission plans, NASA intends to send humans to the moon again by 2024, with special interest in a sustained human presence on the lunar South Pole. There is a need for energy on the moon if people are to stay there, and the sun is a viable source.
Hi, my name is Daniel Guerra, and I'd like to talk about how a solar concentrator could be used on the moon. Well, there are some astounding possible applications. It could be used to supply electricity and lighting for a possible human habitat, or to cultivate plant life on the Artemis base camp. There also exists the possibility of using thermal energy to decompose lunar regoliths producing helium-3 and oxygen. Helium-3 is a light-stable isotope that is currently being developed as fuel to produce energy by nuclear fusion processes. Designing a solar concentrator for applications on the moon comes with its own unique challenges. These challenges include a hostile vacuum environment with extreme temperatures and lunar dust. Lunar dust is composed of very small abrasive particles that float around on the moon's surface, sticking to almost everything. This is problematic for devices with moving parts because once exposed, it will lead to rapid degradation of the device. This means that solar concentrator designs that use mechanical tracking will quickly fail on the moon. A separate issue with lunar dust is that it will also collect on optical surfaces and obstruct light transmission. Now that we have discussed the challenges, let's go over the objectives of our design. Our design abstract requires 30% energy efficiency, and as mentioned previously, the concentrator must not have moving parts and be able to endure extreme temperatures. The optical surfaces must be durable enough to resist scratches and strong enough to endure the stress of a launch. And lastly, the optical surfaces must have minimal lunar dust accretion.
Our design concept incorporates 2 main components, a cylindrical Fresnel lens and a funnel-shaped receiver lens. The cylindrical Fresnel lens is the means by which this design removes solar tracking. As the sun moves across the sky, this Fresnel lens focuses its rays onto the circular edge of the receiver lens. It is able to collect and focus light from a complete range of angles that span 360 degrees. The design could also be turned on its side as seen in the bottom picture for a possible lunar South Pole application, where the sun rotates horizontally around the horizon. We considered the following measures when we optimized the cylindrical Fresnel lens. The lens needs a small focal length, which reduces the circumference of the cylinder without losing any light. Additionally, the team attempted to maximize the width of the lens to capture more sunlight. The focal spot of the Fresnel lens should be no wider than the edge of the receiving lens to minimize lost light. And we also attempted to maximize the percentage of rays that converge in the focal spot. This included taking measures to minimize aberration, which occurs when rays cross at points other than the focal spot. After testing over 20 different designs, including many with aspherical curvature and designs with grooves facing inward, the team arrived at this design for the Fresnel lens. We ended up with a Fresnel lens that focuses parallel light rays to a focal spot that is 12.5 millimeters wide and concentrates 698% of the original energy density onto the receiver lens. This design is scalable, but this particular model has 844 millimeter diameter and a lens profile width of 253 millimeters with a mass of 7.7 kilograms.
My name is Ryan Ellinger. I would like to present the second lens in our system. We call this the receiver lens. Light enters through the yellow edge shown in the left image. This edge is placed directly at the focal spot of the larger Fresnel lens, and once light enters, total internal reflection redirects the light through the tube into a fiber optic cable. This is a simulation of our Fresnel lens and receiver lens system. Here you can see light rays travel from the Fresnel lens towards the receiver lens and into the funnel. Total internal reflection then occurs as light rays reflect down the tube and out the other end. This Pew analysis chart helped the team determine the best material for our lenses. Each column lists a different material property. The range of values from each column were divided into a 5-point system, where most desirable is 5 points and least is 1 point. The team was excited to discover ALON, or aluminum oxynitride, ranked the highest. It is the hardest material on the list, which will help prevent abrasions and fractures on the lenses. Also, its coefficient of thermal expansion is well beyond withstanding the thermal cycling on the moon. At 2423 Kelvin, Alon has a very high melting point, which will prove useful under extended periods of exposure to concentrated sunlight. And although Alon has the highest density of all materials in the chart, this is offset by its refractive index. Because Alon has such a high refractive index, the size of the Fresnel lens is greatly reduced, and the receiver lens is able to retain more light, which improves the system efficiency.
The team used Optica EM simulation software to run optical simulations of our design in Wolfram Mathematica. The capabilities of Optica EM software are quite impressive. Here, we were able to input Alon's refractive index data from a technical datasheet into Optica, and then Optica created a function by fitting a curve to that data. This function was then applied to our lenses when we assigned the medium Alon, as seen here, allowing for accurate results at any wavelength of light. Speaking of wavelength, the most prominent wavelength of electromagnetic radiation on the moon is 0.475 microns. We ran our simulation with 0.475 micron light rays as seen here. For the shape and pattern of our light rays, we chose a line of parallel rays. The sun rays that hit a given location of the moon are practically parallel, and the line-shaped cross-section of those rays was able to give us the needed information in our simulations. Optica EM also enabled the team to turn on Fresnel reflection equations. These equations are vital to determining accurate and realistic ray intensities, as are seen in this intensity plot. The ray colors show the ray intensities from red, most intense, to blue, which is least intense. The team tested over 30 different design options. Optica's STL importability enabled us to test our lenses. We were therefore able to create different variants of our lenses in Onshape CAD software and import them into Optica for testing. Two of the desired Fresnel lens parameters are a short focal length and a focal spot of 6.35 millimeters or less. We were able to use a fine focus function in Optica to evaluate the back focal length and also the focal spot sizes of our Fresnel designs. We created intensity plots and used the find intensity function, which allowed us to evaluate surface intensities, the number of rays meeting a surface, and the transmitted energy through the optical system. This data is crucial in determining the efficiency of the system.
Based on our intensity data from Optica EM, we were able to determine that the Fresnel lens concentrates sunlight at 698%. We were also able to measure that our total system operates at an efficiency of 37%, which exceeds the abstract requirements.
Alon is a very strong material that can handle up to 700 megapascals. This von Mises stress test shows that our Fresnel lens could endure much greater forces than the 9Gs that are typical of a space shuttle launch. While the team is excited about our results so far, more can be done to take this design even farther. Forward work includes further adjustment of the Fresnel lens to improve the focal spot and optimizing the sizes of both the Fresnel and receiver lenses for maximum efficiency. As shown in the picture, it could also prove useful to add mirrors to increase the system's energy output. Lastly, there is still a need to synthesize a method to mitigate lunar dust accretion on optical surfaces.
In conclusion, it has been a fun and interesting journey to work on this design challenge. When we look at all that was accomplished, we are pleased with our results. Our mentor, Mr. Mendel, presented a working prototype of this design concept to the team, and it was satisfying to confirm that this design works using simulation software. The sun offers great potential as a source of energy, and it is our hope that this idea can be used to take mankind even farther, whether here on Earth or on the moon. The SJC Gators would like to offer a sincere thank you to Dr. Nathaniel Wiggins, Mr. Christopher Mendel, Mr. Houston Green, and Dr. Donald Barnhart for their support and guidance. We would also like to thank the Texas Space Grant Consortium and San Jacinto College for giving us this opportunity.